Welcome all. I'm Raji, working as Assistant Professor in Department of Computer Science and Engineering. Today's topic is image transforms. So I'm going to tell you how we are going to convert an image from one representation to the other representation, right? One form into the other form. So that is what you're going to discuss in today's topic. First, we'll listen to what is the representations available for representing a discrete image. Okay, so you have two different representations, matrix representation and singular value representation. So usually what we do it is we represent an image as a function. How do we represent it is f of x comma y, and when you represent that, what happens? X and y are the coordinates, and f means the amplitude of f represents the intensity of a particular color. So that you call it as a pixel value. So usually f of x comma y will be represented in pixels. But in some cases, what happens is there comes some necessity where you will be in need to represent an image either in a matrix form or in a singular value form, right? So to represent a matrix image in a matrix representation, we make use of discrete Fourier transform. And what is discrete Fourier transform and what are its type we are about to see today. In discrete Fourier transform, again you have one-dimensional discrete Fourier transform and two-dimensional discrete Fourier transform. So one-dimensional discrete Fourier transform you are going to make use when you have only one variable representation in your image. If you want two different variables to be represented, uh, uh, two different variables to represent an image, then you can go for two-dimensional DFT, right? So you make use of discrete Fourier transform, and in discrete Fourier transform you have two different kinds. One, it is one-dimensional discrete Fourier transform, and two-dimensional discrete Fourier transform. And the second thing that you have it is singular value representation, where you are going to represent the image using only values like discrete values. For that, what we do is we make use of singular value decomposition transforms. Apart from these discrete Fourier transforms, SVD transforms, you have Haar transform, Walsh transform, here transform, KL transforms. There are several transforms that you can make use. So when there are that many transforms available, why do we concentrate on Fourier transforms? So that we need to know. Why do we concentrate on Fourier transforms? It is because when you convert an image into another form and when you try to reconstruct the image, there will be no loss of information when you make use of discrete Fourier transform. Means discrete Fourier transform helps you to get lossless image reconstruction. That is why we make use of Fourier transform, right? And now we will check what is an image transform and how it is going to be carried out. So before that, we'll just see how the transformation is going to take place. So as I told you already, a transform is nothing but a converting an image from one form to the other form. So usually what happens, I used to represent an image using f of x comma y like this, right? So f of x comma y, this is the representation of an original image. So from this image, what I am going to do, I am going to apply a transform to this particular image, f of x comma y, and I am going to construct t of u comma v. So and what is the transformation that I am going to apply on this particular image? It is r of x comma y comma u comma v, right? So this you call it as a forward transformation function or a forward transformation kernel. And what it is going to do is it is going to combine the parameters x comma y and u comma v, and it is going to construct a new transformation function which you call it as t of u comma v. In other name, you can tell that an image from f of x comma y is being operated upon a function r of x comma y comma u comma v, and it has been transformed into t of u comma v, right? And now we go for inverse transformation, and this process you call it as the reverse operation of a forward transformation. So what you're going to do here, you're going to reconstruct the image. So what you have done here is you have constructed the image into another form, and in this inverse transformation what you're going to do is you're going to take this particular function, transformation function, somewhat you have converted, some that converted image will be there, right? That converted image I'm going to consider, and for that I'm going to apply an inverse reverse function. Okay, so inverse transformation function, and applying by applying this inverse transformation function I am going to get f of x comma y, which is the original image. So you can now understand, after converting the original image into some transformation, now what I'm going to do is I'm going to convert that transformation function into a original function. So this you call it as the reverse process of forward transformation function. So let us recall once again. The forward transformation is the process of converting an image into a transformation function, right? So it can, the transformation function. And what is inverse transformation? And this inverse transformation is going to be the process of converting the converted image into an original image, right? So this is what we call it as inverse transformation. So now let us see the process how the transformation domain is going to take place. So here we have two different domains. The first one is spatial domain, and the second one it is transform domain. Now let us start with spatial domain. What is spatial domain, and what is the things that has been represented in the spatial domain? So spatial domain is nothing but the domain where the image is being operated as pixels, right? Only with the pixel representation we are going to perform the operations in spatial domain. As I said already, it's a recap. What we are going to do is we will not be able to apply all the tasks of the image as pixels. Sometimes instead of using pixels, we need real-time values to operate. So we convert the image in spatial domain into a transform domain by applying some transformation function, right? So f of x comma y is going to be in a spatial domain which represents an image, and that image is going to be represented in terms of pixels. So in this, now we are going to go for the transform part. So you have an image which is being represented using pixels. You apply that and you give that into a transformation function, right? So you apply some transform so that the image which is represented in pixels is being converted into transform t of u comma v, and this is the transformation function. So now once your image has been converted, which means which is suitable for some operation, you can perform that operation on the transformation function t of u comma v. You are going to perform that operation on t of u comma v, right? So now after performing that particular operation and how it is going to be represented, you have performed the operation r, right? Where this operation is being performed on the transformation function t of u comma v. So this is the transformation function on which the operation r has been performed. And this output from this part, what you're going to do, you're going to reconstruct the original image. Now for reconstructing, what you need an inverse transform. So in this transform part, you're going to apply a transformation function to convert your original image into a transformation function. And here in the inverse transform, what you're going to do is you're going to apply some transform to the transformation function to convert that into an image representation. So here you can see, I'm telling you that you're going to reconstruct the image, I always be speaking about reconstruction. But what happens, what I have represented, instead of representing it as f of x comma y, I have represented it as g of x comma y, right? Instead of mentioning it as f of x comma y, what I have represented it as g of x comma y. So why is it? So b of f of x comma y means it is going to be the original image, and g of x comma y, it is the image after some operation are being applied. So to be simple, let us consider f of x comma y is an original image that you have taken, and after applying filter, just either the background or the intensity level might be changed. There might be very slight changes in the image. So this f of x comma y with slight changes or with the necessary operations that has to be performed after getting done, you reach the image g of x comma y, right? So that is why instead of representing it as f of x comma y, we make use of g of x comma y, right? And now before going for the other transforms, like what are the transforms that we have seen? It is discrete Fourier transform and SVD transforms, right? Instead of measuring those before going to those transforms, what we are going to do is we are going to listen to the basic concepts that are needed. So the basic concepts that we need is we are going to know about what is a complex number and what is a conjugate of the complex number. So here first we'll tell you what is a complex number. A complex number C is represented as R plus Ji, where R and I are real numbers, right? And here J is going to be a number which represents, it is an imaginary part which is equal to -1, and C star is equal to R minus Ji, right? So C star, which represents the conjugate of a complex number, is going to be a conjugate of a complex number, right? So now we'll identify what is a complex number and what is a conjugate of a complex number. Okay, so I said already, complex number C is equal to R plus Ji, where R and I are real numbers. In conjugate of a complex number, we represent that to be C star is equal to R minus Ji. It means conjugate of a complex number is obtained by the from the original complex number by changing the sign of the imaginary part. In case if you have the complex number to be R minus Ji, then the conjugate of your complex number is going to be C is equal to R plus Ji, right? So it gets inverted. So here what you're going to do, you have a representation for complex number, and the complex number is from that complex number you're going to construct, or you're going to get a conjugate of a complex number by changing the sign of an imaginary part. And now we'll go for the Fourier series theorem. So before going for the Fourier transform, we need to know what is a Fourier series theorem. Okay, so this you would have read in mathematics, but let me tell you once again. Okay, so Fourier series theorem, and where you use this theorem and when you use this theorem is like, so you use this theorem when you just want to operate on any signal by varying its frequency. Okay, so you want to vary a frequency of a sine wave or a cosine wave, you can make use of Fourier series theorem. Okay, so as said already, how the image is going to be represented now, it is going to be represented by f of x comma y, so which is going to be a function, right? So f of x comma y is going to be a function. When you take analog values, you call that to be analog function, and when it is going to take digital waves, you call that to be a digital signal. Either it is going to be an analog signal or it is going to be a digital signal, right? So that's what is going to happen. And now Here we are going to see like any periodic function you have f of t. So that is the signal that which you are going to vary with respect to frequency. After you are going to obtain after varying the frequencies. So and that can be expressed as sum of sine and cosine waves, which is going to be an infinite sum. So to tell that it is going to be an infinite sum, we make use of infinity, right? So you know only from this particular place I am going to start. It means I know only the starting place and I'm not sure about the ending part, right? So what I'm going to do, f of t is equal to a naught plus sigma n minus 1 to infinity an cos n f naught t plus sigma n minus 1 to infinity bn sin n f naught t. So this equation represents the Fourier series theorem. And here A naught is going to be a constant in the first term. Now let us consider the second term that you have sigma n minus 1 to infinity a n cos n f naught t. And here we'll see term by term. So you will have sigma which represents summation, right? So the addition of all the other values like a n cos n f naught t, where I'm going to give the range for n. F naught is going to be the fundamental frequency and t it is going to be the time, and with which part you are going to vary, which is we are going to vary it with frequency. So instead of a n I'll substitute like a of n minus 1, a of n minus 2, and so on it goes. You can substitute any values for n. Okay, so the values that you're going to have, the summation part is like it is going to be applied for n. Instead of n, I can start applying the values from n minus 1 to infinity. As per the definition, what is this part? It is weighted sum, like infinite sum of sine and cosine, right? So first we have the cosine sum here, so cos n f naught t, and to tell that it is an infinite part, you make it as n minus 1 to infinity. Only the starting point I am mentioning, because it goes till infinity, we have mentioned the other end as infinity, plus the we'll go for the other sum now, which is equal to sine wave, right? So cosine sum we have already mentioned. Infinite cosine sum has been represented as sigma n minus 1 infinity a n cos n f naught t, right? Similarly we go for sine function. Sine function, we have a constant again which is being represented as Bn. Similar to cosine wave, we are going to have, we know about only the starting point. So the starting point is going to be n minus 1. And the ending point is again infinity. So we mention it to be infinity. And to for where you are going to apply these values, n minus 1 to infinity in the place of n. Instead of Bn, I am going to apply it as b of n minus 1, b n minus 2, b n minus 3, and so on. At some particular point you will have some constant values and it extends till the infinite values, right? So is that clear? So in Fourier series theorem, where you are going to apply, you are going to apply in the place where you want to vary a signal with respect to frequency. Okay, and that can be expressed in terms of sum of infinite sum of sine and cosine functions, sum which represents infinite sum only, right? So if I'm going to refer it as sum of sine and cosine functions, it obviously means that it represents infinite sum of sine and cosine functions with varying frequency. So this is the Fourier series theorem with which we are going to derive the Fourier transform, right? So this, if this Fourier series is clear, now we can go for the Fourier transform. And what we are going to do in Fourier transform? So again, as said already, Fourier transform is going to be a continuous signal. So it is going to transform a signal from the spatial domain to the frequency domain, right? So this is going to transform a signal or a function from spatial domain to the frequency domain. So to differentiate the domain, we make use of two different characters. to mention that it is a function in spatial domain, we make use of x. F of x means that function in spatial domain. F of u means that it is the function in frequency domain. Right? So this continuous Fourier transform is going to convert a signal from spatial domain to the frequency domain. So similar to the transform pair what we have seen already, we do have forward Fourier transform here and inverse Fourier transform also. Okay. So the Fourier transform here, what I'm going to represent in caps, what we have here is the Fourier transform. So it tells that here I'm going to apply this Fourier transform onto the function f of x, which is a function in spatial domain. Right? F of x is a function in spatial domain, and I am going to apply this forward transformation on this function. After applying the forward transformation, and how I'm going to represent that, it is going to be represented as f of u. Why do I represent that? Once you apply the transformation, this particular function gets converted into frequency domain. So to tell that now the signal is being there in the frequency domain, you write it as f of u. And now we'll see the function used to convert the transform into from spatial domain into frequency domain. This is what we have seen. F of x e power minus j 2 pi u x. So here with respect to the frequency x, so that is what the function has been represented, right? It is f of x. So I am going to integrate the function with respect to x. So I am going to integrate the function with respect to x. And what is the levels from where I am going to start and where I am going to stop? That depends on the signal after I choose. So from infinity level in the negative part to the infinity level in the positive part, I can continue. Means this is the transform where the function in a spatial domain has been converted into a function in the frequency domain. So since it is in the forward part, you call this to be a Fourier transform. And now we'll go for the inverse Fourier transform. And in the inverse Fourier transform, what we are going to do? The reverse function. It means we are going to convert a function which is there in the frequency domain into a function which is there in the spatial domain. Right? So and now, so what is the to tell that you are going to apply inverse Fourier transform? We make it use of F inverse. Right? So I'm going to make use of F inverse here. So after F inverse, I'm going to make use of F of u, which means I'm going to apply an inverse transform on the function f of u. So that was the result after applying Fourier transform, like forward Fourier transform. So here what I'm going to do, I'm going to apply inverse Fourier transform on that particular function. And after applying that function, what should be my result? The original function should be derived. So it is equal to f of x. And how do I derive that function? It is again an integration of the transform function which I have got already, f of u into e power j 2 pi ux. As I said already, it is going to be an inverse Fourier transform. So where you have mentioned here, it is f of u into e power j 2 pi ux. Instead of minus j 2 pi ux, I just make use of e power j 2 pi ux. And with respect to u, I am going to differentiate this function because it has already been there in the frequency domain. It is not now, it is not there in the spatial domain. It is now there in the frequency domain. So I am going to integrate this function with respect to the frequency du. Right? So this is what you call it as continuous Fourier transform. Right? In this transform part, what you have forward Fourier transform and inverse Fourier transform. This together, whatever transform you take, every transforms, what if it, even if it is going to be the discrete Fourier transform, or if it is going to be SVD transform, or if it is going to be KL transform, all the transforms are going to have two different equations, right? One equation, it is to convert your a function from the spatial domain to the frequency domain. It differs, and that particular equation differs based on the transforms that you choose. So here, what the equation what I have represented is for continuous Fourier transform. For the continuous Fourier transform, you make use of the integration minus infinity to infinity f of x e power minus j 2 pi ux into dx. This is the equation for converting a function from spatial domain to frequency domain in continuous Fourier transform, right? And you have to notice one more thing. In continuous Fourier transform, how many variables we have used here now? Only one. So because we have operated on only one variable, you call this to be one-dimensional Fourier transform, continuous Fourier transform, like one-dimensional continuous Fourier transform. The other case, what you can do is you can make use of two variables, x and y. And similarly, when you represent the same in frequency domain, you go for u and v, right? So when you make use of two different variables like x and y, which refers to spatial coordinates, and u comma v, which refers to the frequency, you can call that to be two-dimensional Fourier transform, right? So what do you call? You call them as two-dimensional Fourier transform. So if you are going to operate on only one variable, then you choose one-dimensional discrete Fourier transform. And when you try to operate on two different variables, you make use of two-dimensional discrete Fourier transform. So and whenever whatever transform you're going to make use, you're going to have two different equations. What are those? One equation which we call it as forward transformation, and the other equation which you call it as inverse transformation. And the forward transformation, what it is going to do? It is going to convert the image from spatial domain to the frequency domain. And the inverse Fourier transform, what it is going to do? It is going to convert the signal from frequency domain to the spatial domain. So these two equations, like the forward transform function and the inverse transform function, together you call it as a transformation pair. A transformation pair. What is a transformation pair? It is a combination of a forward transformation equation and the inverse Fourier transform equation. These two equations together you call it as a transform pair, right? So now, so whatever transformation you take, so for all the transformation, this particular pair is necessary to carry over the next coming steps, right? So I think it will be clear. So I'm repeating the last thing again. So when you go for any transform to convert a signal from spatial domain to frequency domain, you are supposed to have a a transformation pair for compulsory. Without a transformation function, you will not be able to continue. So a transformation pair, which means the combination of forward transform and inverse transform, is necessary, right? So with this, I am concluding my topic. Thank you.